All right, this section, 7.1, we moved from chapter 6. We did sections 6.1 and 6.2 on solving trigonometric equations. And now that's all we're doing now in chapter 6 in this last section. Now we jump to chapter 7 where we're going to look at solving triangles. And so we've already early on learned how to solve right triangles using their 6 trig functions. This section, you may remember a lot of it from Algebra 2, is going to review how you solve non-right triangles or oblique triangles, another name. So remember that each triangle has 6 parts, 3 angles, 3 sides. In order to be able to solve a triangle, we have to know at least 3 of those 6 parts, and it has to be a certain combination of those three parts. And this table summarizes what combinations of parts allow you to solve the triangle, and if you have those 3 parts, which method you would use between law of sines and law of cosine. So the very first one to make note of is that angle is not gonna, having the 3 angles of the triangle is not gonna let you solve, it's not gonna allow you to solve the triangle, because there's multiple triangles that can have the same 3 angles. If you remember this from geometry, angle doesn't give you congruent triangles. You can have several different triangles that have the same size angles, and they're totally different triangles. So this doesn't give you a unique triangle, and it would not be solvable. If you have a case of 2 angles and a side, whether the side is between the 2 angles or not, you will be able to use law of sines on those. If you have 2 sides and the included angle, meaning the angle between the 2 sides, or if you have all 3 sides, those are cases where you would be able to apply the law of cosines to solve the triangle. And then you have this final case, which we'll spend in, I think, section 7.3, we look at side-side angle. Okay, if you remember this one from geometry, this is the one that did not guarantee congruency. So you may have 2 triangles where you know 2 sides and a non-included angle of one triangle, and they may be congruent to 2 sides and a non-included angle in the other triangle. Did not guarantee those triangles would be congruent. This is called the ambiguous case. So what can happen if you have a triangle where you know 2 sides and the angle that's not between the 2 sides, it could be, from that information, there could be one triangle, there could be 2 triangles that have those parts, or there could be no triangles that have those parts. So it's ambiguous because we don't really know. You have to look at each on a case-by-case basis to determine, is it a case where there is no triangle that works with those sides and that angle? Is there one triangle, one unique triangle that works, or is there 2 different triangles that can have those 2 sides and that one angle? In that case, you would have to look at both. There could be 2 answers to that problem. Okay, so in this section, we're strictly going to look at law of sines. We're going to look at cases where you know 2 angles and a side, and how you use law of sines. So at the side here, I'm going to write, if you remember from Algebra 2, law of sines says that side A over the sine of angle A is equal to side B over the sine of angle B is equal to side C over the sine of angle C. So you can use any combination of 2 of those ratios to make a proportion that you can solve. And note that it would be the same thing if I put sine of A over side A equals sine of B over side B equals sine of C over side C. I could turn those over, it'd be the same thing. Okay, so let's jump into an example here. In example 1, we're given angle B. Let me just draw the triangle here. So triangle ABC, and I'm not going to necessarily draw up scale. Let's say A is here, B is here, C is here. Angle C is 82 degrees, labeling what I know. Angle B is 34 degrees. And side A, remember side A is always across from angle A, and it is 5.6. We use lowercase letters to represent the sides and capitals to represent the angles. So when you see a capital A, that means angle A. When you see a lowercase a, that means side A. All right, and so we are trying to find the length of side B. So let me just label side B across from angle B there. So using my law of sines formulas, knowing I'm looking for side B, so I'd have to incorporate little b since that's what I'm trying to find. And so B over the sine of angle B equals, I can't do C over the sine of angle C because I don't know C and I can't have two unknowns. A over the sine of A. Now you may say, well, I don't know angle A. Well, I really do, because we know there's 180 degrees in the three angles of any triangle. So if we just add 82 and 34, that is 116 degrees. And so from 180, that leaves us 64 degrees for angle A. So I really do know this angle. So angle A, so I found that. Okay, so now I can say that A over the sine of angle A. So I don't know little b, that's what I'm trying to find, side B. I do know angle B. I know side A, and I know angle A. And so if I'm solving this for B, I simply have to just multiply both sides by sine of 34 degrees, and multiply this side by the sine of 34 degrees. And so my answer, B, is going to be whatever 5.6 times the sine of 34 degrees divided by the sine of 64 degrees. And then I could just put that in my calculator. It doesn't really specify where to round, so let's see. So 5.6 times the sine of 34 divided by the sine of 64, and I get about 3. I'll just round to the nearest tenths place, about 3.5. And if I'm only looking for side B, then I'm done. So I really have solved the triangle all except for side C. It didn't ask me to find that side. All right, example 2, very much like example 1. Just to kind of get back in the groove of this, let me draw this out again. So I have angle A to be 46 degrees. Angle B is not given. Angle C is 78 degrees. So I do know angle B because I can use the 180 degree rule. So 78 plus 46 is 124 degrees. And 180 minus 124 is 56 degrees. So angle B here is 56 degrees. Now the sides I know is B. B is 7.5. And it says find the missing parts of triangle A. So basically it's saying solve the triangle. Well, I know everything. I know all three angles. I know one side. So it really just leaves me these two sides to find. So I need to find side A. I need to find side C. So we have kind of two jobs here to solve the triangle. And so I could start with either one of them. I'll just start with A. So I'm going to say A over the sine of angle A. And so instead of just saying sine, I'm going to go ahead and put in the angle, which is 46 degrees. So A over sine of A is equal to B over sine of B. So 7.5 over the sine of 56. Now you couldn't do C at that time because you can't have two unknowns. You're going to have two different problems to find A, and one to find A and one to find C. The one I would use, I could say 7.5 is to sine of 56. That's B is to the sine of B, as C, what I'm trying to find C here, is to the sine of. So this proportion would work to find A. This proportion would work to find C. I would multiply both sides by the sine of 46 here. So 7.5 times the sine of 46 degrees divided by the sine of 56 degrees. So just multiply both sides by sine of 46. Put that in my calculator, and I will have A. In this one, I would multiply both sides by the sine of 78 degrees. And so C would equal 7.5 times the sine of 78 degrees divided by the sine of 56 degrees. Again, put that in your calculator. 7.5 times the sine of 46 divided by the sine of 56 is 6.5. And again, we'll just keep with the significant digits there. And to find C, 7.5 times the sine of 78 divided by the sine of 56 is 8.8. And so I now have solved the triangle. We now know all three angles and all three sides. Okay, so in these remaining examples, we're just going to look at some applications. Basically the same thing you did in examples 1 and 2. It's just going to be put more into the context of a real problem. So you can read the problem yourself. I won't read through it and bore you with that, but bottom line is this is a track and field event where the shot put, and this is the shot put ring. So the athlete stands in the ring, and they usually, if you've seen them do that, they turn and turn until they get to the very edge. I think they put their foot up to the line, and they throw the shot put as far as they can, and the object being to throw it the furthest. In this, it talks about where the shot put lands. It usually makes a little divot in the ground, and so they put a little device on that, in that divot, and that device calculates the measure of this angle A and this angle B. This distance from the shot put ring to the observation booth is always, that would be measured, have been measured ahead of time, and so they would be able to use the off signs to do the math to figure out from the booth how far the throw was. So given in this particular example, to find the distance, use the law of signs to find the distance x. So we want to find how far they threw the shot put, how far it landed from the ring. If A, which is the distance from the ring to the booth, is 738 feet, the angle B is 6.3 degrees, and the angle A is 78.4 degrees. And so we are looking for S, the distance that they threw the shot put. And so again, I have a case of angle, angle, side, 2 angles in a side. I'm going to be able to use law of signs. I know that this side over the sine of this angle will equal this side over the sine of this angle. So the side, 738, divided by the sine of the angle opposite that. If it helps, you can always label these A, B, and C and keep up with everything. Equals S over the sine of the angle opposite that, which is 6.3 degrees. And so it's just same thing we did in example 1 and 2. We'll solve by multiplying both sides by 6.3 degrees. So S is going to simply be equal to 738 times the sine of 6.3 degrees divided by the sine of 78.4 degrees. And that would be the length of the throw. Let me put that in my calculator here. 738 times the sine of 6.3. And then I divide that by the sine of 78.4. And I get 82.6, sorry, 82.7, we'll round up there, feet. And that would be the distance of the throw. So nothing different. Same old thing you did in examples 1 and 2, just put into the context of a real problem, real world problem. Okay, example 4. Got to do a little bit more work in this problem than we did in the previous problem. It's still a law of signs problem. It's still it's a real world type problem, but it's not quite as cut and dry. Really simply because look at what we're trying to find. So this is a satellite is circling above the Earth. So here's my satellite. When the satellite is directly above point B, so that's when it's directly above point B, angle A is 79.2 degrees. So this angle, go ahead and label this in here, is 79.2 degrees. The distance between points B and D on the circumference of the Earth is 1,050. So this arc length right here is 1,050 miles. And then we're given the radius of the Earth. This is the center of the Earth to be 3,960 miles. And that shows the radius at 2 different places there. So the problem at this point is I have this angle, one angle, and I have these 2 sides of this triangle. Now, I do see, I'm trying to find this distance from A to B here, how far the satellite is from the surface of the Earth. That's not going to be a problem if I can find the length of the side of the triangle, I would just subtract the radius of the Earth, 3,960 from that. So let's focus more on the entire triangle. And so the question is, can I find the side of the triangle? Okay, well, with one angle, no, I can't at this point. So I could do law of sines if I knew another angle. And so one thing I do see is, so I've got I know this arc length right here. And if you remember from geometry, the central angle of a circle, which is what this is always equal to the arc it cuts. So this angle and this arc would be equal. So I know that this arc is, I know the actual length of it is 1,050 miles. I can convert that to radians and then into degrees. So right now I actually have arc length, but I know that 1,050 miles is to the radius. A radian is 3,960 miles. All right, so that is going to be how many radians this angle is. And then I want to go from radians to degrees, so I would multiply this by 180 degrees over pi radians. Remember, that's the conversion. I want to end up in degrees, so 50 degrees on top. So basically, this is going to be, let me go ahead and calculate how many degrees this angle is from that then. So it's 1,050 miles divided by 3,960. That's what a radian is. So it's basically 0.265 of a radian. That's how many radians the angle is. That's what 1,050. So this is 0.265 of a radian. A radian is 3,960. All right, times 180 over pi. So in degrees, this is going to be 0.265 times 180 degrees divided by pi radians. Comes out to be about, I'm going to carry it out to 15.2 degrees. Okay, so this angle C in degrees here is 15.2 degrees. So I just had to use the arc length. I can convert that to radians and then to degrees. And so I've got the angle C in degrees. Now, I should be able to set up my law of sines. So, well, let's go ahead and find the third angle. So I know this angle is 79.2 degrees and this angle is 15.2 degrees. And so that means that two of my angles add up to 94.4 degrees. And so 180 degrees minus 94.4 is going to be 85.6 degrees. All right, so this angle, D, here is 85.6 degrees. All right, so this is the side of the triangle that I'm trying to find, because if I know that side, I can just subtract the radius of the Earth, 3,960, and I'll know how far the satellite is from the surface of the Earth. So the trick is to find the side. And I should be able to use law of sines at this point. So let's go with the side. I'll call it X, since it's unknown, is to the sine of the angle opposite that. As this side, 3,960, is to the sine of the angle opposite that, which would be the sine of 79.2 degrees. And then I just simply multiply both sides by sine of 85.6. That'll divide out over here, and it will allow me to then solve for X. So 3,960 times the sine of 85.6 divided by the sine of 79.2 is 4,019.5 miles. Now that's the entire side. Of course, we don't want the entire side. We want to know how far it is from A to B. In other words, how far the satellite is from the surface of the Earth. So I would take 4,019.5 miles and subtract from that the radius of the Earth, 3,960 miles. And I get just double check my, 59.5 degrees. Or not degrees, miles. I forgot what I was solving for. So the distance that the satellite is from the surface of the Earth, and there was distance from A to B, is 59.5 degrees. Miles, I keep saying degrees. 59.5 miles. Okay, example 5. The diagram's a little complicated looking here, but let's kind of go through the problem and look at what's labeled and set up on the diagram here for you. So we have a hot air balloon. It's flying over a dry lake. And when the wind stops blowing, the balloon comes to a stop 450, this should be 450 feet above the ground. At point D, and this is the figure, it's referring to figure 9. All right, so here's my hot air balloon above the ground, 450 feet above the ground. All right, Jeep following the balloon runs out of gas at a point A. So here's the Jeep coming along, runs out of gas here. The nearest service station is due north of the Jeep at point B. Now, you may think, why did they not draw it? This is in 3D. Remember, the balloon is up in the air, and the Jeep and the service station could be on the ground. So here's your north-south line. Here's your east-west line. So we're three-dimensional here. And the balloon, the red there, is kind of should be coming up. This is ground level, so that's showing the 3-dimension there. But the Jeep, let's see, the bearing of the balloon from the Jeep. So here's the balloon, here's the Jeep. So is 13 degrees east of north. So this is the north line, so east of north would be that side of the north line. So that angle is 13 degrees basically is what they're giving you. While the bearing of the balloon from the service station at B, so here's the service station, which is due north of the Jeep, and this is the north-south line, is 19 degrees east of south. So this is the south line, east of south would be that way. So it's already labeled for you on there. The angle of elevation to the balloon from point A, so from if you're standing at A, looking up the balloon, that angle of elevation is 12 degrees. How far will the people in the Jeep have to walk to reach the service station at point B? So basically, what is the difference from A to B? So we're looking for this distance right there from A to B, from the Jeep to the service station. All right, so I immediately see this side right here is a side of this triangle. Now, in that triangle, I know the angles. I could find this angle if I needed it. And I've got 2 of the 3 angles, so we know they have to add up to 180. I don't know any sides. Okay, that's a problem because angle, remember, is not enough information to be able to solve that triangle. There's many triangles that can have those size angles. So I got to do something in this problem to be able to find another side of this triangle before I could actually work it. Now, one thing that's jumping out at me is I see this right triangle right here, and this is the right triangle formed by the balloon's distance above the ground, and then the angle of elevation to the balloon. So just focusing on that right triangle right there. I have the angle. Let me pull just that triangle out over here. Let's draw it. All right, so here is my balloon at point D. Here is my Jeep at point A, and point C is just the distance, the spot right on the ground below there, on the water, whatever, right below the balloon. And so we know the distance the balloon is above ground, and we know the angle of elevation to the balloon. Well, looking at that and just going back to, chapter 1, chapter 2 stuff, solving a right triangle, we can do that. I can find this side or this side, either one that I need. Well, side AC is also a side of this triangle, and that would give me, so this is my trick right here. If I can find this side, because it's also a side of the right triangle, then I will have a side of this oblique triangle, and I'll be able to solve for x or any whatever I need. So how can I solve this? It's AC is the side I need. Okay, well, I could just use a basic tangent function. Opposite, I know the opposite side. I'm trying to find the adjacent side of the angle 12 degrees. So I could say the tangent of 12 degrees is equal to 450 feet divided by x. So if I multiply both sides by x and divide by the tangent of 12 degrees, I get, let's see, the tangent of 12 degrees, no, I'm sorry, 450 divided by tangent of 12 degrees is 2,117.1 feet. Okay, so this side now I know. All right, so focusing now on this triangle ABC, I can use law of sines. I'm trying to find x, which is the side across from this side. So I could say 2,117.1 divided by, well, this side is across from this angle. So divided by the sine of 19 degrees is equal to x. So I have to include x since that's what I'm trying to find. But that's the side across from angle C. I don't have angle C, but I can find that because it's just 180 degrees minus 19 plus 13, which is 32, which makes that angle 148 degrees. So it would be by the sine of 148 degrees. So x over sine of 148 equals 2,117.1 over sine of 19. If I solve that, then I know the distance from the Jeep to the service station. So I would just simply need to multiply both sides by 148 degrees. And the rest my calculator will take care of here. So 2,117.1 degrees times the sine of 148, and then divided by the sine of 19. And I get 3,445.9 feet. And that would be the distance from the Jeep to the service station. All right, so in this example uses some knowledge of vectors, which we did not cover that section. So I'm not going to get into all the vector details, but they've given you basically the outline of that drawing, the diagram of it, and you can answer this question without really understanding a whole lot about the vectors and how that works with vector addition. And so basically we have a traffic light. The traffic light is hanging, and the weight given for the traffic light is 22. So this vector is going to be representing the weight of the traffic light, while these two vectors are going to be representing the tension of the two wires that are holding that light. All right, and it's given to us, I think everything that we need is on the diagram, so yes, okay. All right, so we are looking for the magnitude of the tension in wire AB, which is T2. So this is A, B. All right, so the original drawing, let me kind of draw that so you can see that. So here was the traffic light. And these are the tension wires. This is C. And this is point A. All right, so AB, we're trying to find the tension in wire AB and the magnitude of the tension wire. Oh, we're trying to find both, okay. So we're trying to find both T1 and T2. Okay, so basically they have, the part that you might not know is from our not doing the section on vectors is how this was drawn from this. But let's just go with this drawing. The two wires is what we're trying to find, T1 and T2. On the triangle, we know this vector is, magnitude is 22. Given that these angles are 45 and 60. This is just an alternate interior angle if you remember from geometry. So this would be 45, and if this is 60, this would be 60, which means that because this is 180 degrees, and that's 45 and that's 60, 105 from 180 means this angle in here has to be 75. We know these angles have to make 180 degrees because that's a straight line. So I basically know all three angles of my triangle in one side, and that's enough. We know from law of sines to be able to solve this using law of sines. So we are looking for, we basically have to do two problems, one to find T1 and one to find T2. So let's do T1 first. So I'm going to say T1 divided by, or T1 over the sine of the angle across from it, which is 45 degrees, is equal to 22 over sine of 75 degrees. All right, and then I would do one for T2. I'd say T2 over the sine of angle 60 equals 22 over the sine of 75. And then I just cross multiply and solve both of those. So this one I'll multiply both sides by the sine of 45. And these I'll multiply both sides by the sine of 60. And so I have T1, let's see here, 22 times the sine of 45, which is square root of 2 over 2, or we'll go ahead and put it in decimal form here, calculator. And then that's going to be divided by the sine of 75. All right, and so the tension in that wire is 16.1. All right, and or if they want significant digits, we just say 16 pounds is how the tension would. Units. So T2 would be 22 times the sine of 60 divided by the sine of 75. And that comes to be 19.7, which will just round up to 20 pounds. This would be significant digits if it asks you to leave it that way. And those would be the tensions of each wire.